Alright, hello. My name is Gantt Meredith, and my exam 3 topic is going to be phase diagrams. So let's go ahead and get started. So what are phases? Before we even think about the diagrams, let's think about what phases are. Normally when we think of phases, we think of solid, liquid, and gas. And if we were to compare this to water, we have solid water being ice, liquid water being liquid water, the kind that we drink, and then gas water would be water vapor. Now, and as we add different pressures and different temperatures, and as the temperature and pressure changes of a given sample of water, we're going to transition between all three states, solid, liquid, and gas. But we'll get into that in a second. Now, for the purposes of this course, we'll actually only be focusing on solid and liquid phases. And one important thing to note with our binary-eutectic systems, which we'll get into later, there are two types of solids now, so it's no longer just one. We have an alpha solid and a beta solid. Now, in order for us to understand binary-eutectic phase diagrams and binary-eutectic systems, it's important to consider a simple phase diagram. So let's look at how the diagram is labeled. At the bottom we have temperature in degrees Celsius, and on the left-hand side we have pressure in kilopascals. Now it's important to note that even though pressure is, the units are given as kilopascals, you can use any units of pressure. So we're talking torr, millimeters of mercury, atmosphere. It does not matter as long as you have a unit of pressure. And at the bottom, when we look at temperature, the same rule applies. We could have temperature in degrees Celsius, Kelvin, Fahrenheit. Again, as long as you have a unit of temperature, that is all that matters for simple phase diagrams. Now, as I was saying earlier, this is a water phase diagram. So at the top left we have solid ice, in the middle liquid water, and at the bottom gas water vapor. So how do we read this? How do we interpret this diagram? Well, let's look at 100 degrees Celsius. If we follow up at this temperature, we realize that once we pass 101 kilopascals of pressure, we enter the water liquid region. What this means is that above 101 kilopascals and at 100 degrees Celsius, we will have liquid present in our sample of water. Now, in addition, we need to look at the lines that are present on the phase diagram. So I'm going to outline 1, 2, 3 lines or curves on our graph. And what do these mean? Well, these demonstrate equilibrium. So along the bottom left curve, for example, we are in between the solid and the gas phase. And this means that at any temperature and pressure along this curve, we will have, in a theoretical lab setting, 50% of both solid and gas. Does this happen in the real world? It's hard to say, but this is at least in a theoretical laboratory setting what we can expect. You'll also notice there are two interesting points on the graph. If we look up at the top right, we have the critical point, and past this point, in terms of temperature and pressure, once we go past 374 degrees Celsius and 22,089 kilopascals, we reach what's known as a supercritical fluid. And it's hard to say if it's a liquid or a gas. It's an indeterminate state, and these can get pretty tricky, but we won't have any of those present in our binary-eutectic systems that we'll talk about next. Now, the other point of importance is the triple point, and this shows equilibrium between all three states. That's why it's called the triple 3 point. Theoretically, again, in a laboratory setting, we can expect 1/3 solid, 1/3 liquid, and 1/3 gas of water present at the specific temperature, 0.01 degrees Celsius, and this pressure, 0.6 kilopascals. Now, when we transition across these boundary points, these phases, we have different phase changes. So, for example, from solid to gas, we have sublimation. If we transfer the other direction, we have deposition. If we go from solid to liquid, that's melting. And if we go from liquid to gas, that's freezing. And then if we go from liquid to solid, that's freezing. If we go from liquid to gas, that is vaporization. And if we go from gas to liquid, that is condensation. You can think about the water cycle, boiling, freezing water, whatever you need to remember the names of these. The two tricky ones are deposition and sublimation, and those have to do with gas and solid transformations, which are not that easily observed in nature. Alright, now we're on to binary-eutectic systems, which are the systems we'll be focusing on for this course. Binary meaning two, and if you look over at our phase diagram, we have copper and silver in an alloy system. Now it's important to notice the axes on this phase diagram as well. So on the right and left hand side we still have temperature. On the right hand side we have degrees Fahrenheit, and on the left hand side they got cut off, but we have degrees Celsius. Now at the bottom we no longer have pressure. What we have is actually composition. We have composition of silver. It's important to note that silver is the reference point for this phase diagram. Now, how do we read binary-eutectic phase diagrams, and how are they different than simple phase diagrams? Well, before we answer that question, we need to understand what eutectic means. And a eutectic system is a homogeneous mixture of substances that melts or solidifies at a single temperature that is lower than the melting point of either of the constituents. One important thing to note with binary-eutectic systems is that we will only have liquid and solid phases in this course. As previously mentioned, there will actually be two solid phases, the alpha phase, which is located right here on the graph, and the beta phase located on the right hand side. The alpha phase is, in this case, is copper with silver in solution, and the beta phase is silver with copper in solution. Now, there are also three types of lines to consider, and the same principles with lines apply from simple phase diagrams to binary-eutectic, but we just have three specific lines that are different in this case. We have the solvus line present in the bottom left-hand corner, and this line indicates the limit of solid solubility. We then have the solidus line in the middle, which is the division when only solid is present. And if you look to the right of the solidus line, we see we only have the alpha solid present. The final kind of line that we have is the liquidus line, and the liquidus line shows the division when only liquid is present. If we pass above this liquidus line, you'll see that we only have liquid present in our binary-eutectic system. Now, there is one special point to note with the binary-eutectic systems, and that is right here. This is called the eutectic point, and the eutectic point is the minimum freezing point, or the lowest melting point of this binary-eutectic system. Now, how do we apply what we just learned to binary-eutectic systems, and what can we expect on the exam? Well, for example, if we were to take 60% silver at 60% silver along this line, this composition of silver. If we were to take any temperature, so let's say 900 degrees Celsius, what can we expect the phase to be? We can expect to have a liquid phase of our system. Now, if we were to go at 800 degrees Celsius, we would expect to have the alpha solid present and the liquid present. And then if we were to drop below, it looks roughly about 775 degrees Celsius, we will have the alpha and beta solids present and no liquids present in our system. This is a very general understanding of the kinds of questions we can expect on the exam when it comes to determining what compositions and what temperatures will yield which phases, either liquid, alpha solid, beta solid, or any combination of those three. And with that, I believe that we have sufficiently covered binary-eutectic systems, and we should be able to begin working through some practice problems on our own to test our knowledge. Thank you.